Welcome back. The next thing we're going to talk about is the matrix transpose and the concept of symmetry. The transpose of a matrix is just another matrix whose rows are the corresponding columns of A. So if A is m by n, then A transpose will be n by m. Let's see an example. Here I have a matrix A that's 3 by 4. Well, A transpose is a matrix that's 4 by 3, where the corresponding rows are the columns of A. Similarly, I could say that the columns of A transpose are the corresponding rows of A. So all we do is switch the rows and columns. Here are some more examples. I have 3 matrices. One of them is a vector. And to find the transpose, we simply create new matrices by changing the rows into columns. So the first row of B is 2, -3, -4, and that becomes the first column of B transpose. You can see the next second row becomes the second column, third row becomes the third column. And the same is true for M transpose, which is now 2 by 4, and X transpose. If X is a column vector, then X transpose is a row vector. A symmetric matrix is a matrix whose transpose is equal to itself. For example, I have this matrix B. B is 3 by 3, and if I take the first row of B and turn it into a column, and the second row and turn it into the column, I can see that I'm actually recreating the same matrix over again because the first row is equal to the first column, and the second row is equal to the second column, and so forth. So this matrix is symmetric because the transpose is equal to itself. To be symmetric, a matrix must be square. This makes sense, right? Because if a matrix was rectangular and we took the transpose, the resulting matrix wouldn't even have the same size as the original. Like these matrices on the previous slides, M and M transpose don't even have the same shape. So it's necessary that a matrix be square to be symmetric. But it also must have this property of this symmetry across the main diagonal. So we talked previously about the main diagonal being the longest diagonal of a square matrix from corner to corner. And the symmetric matrix is called symmetric because it has this symmetry. And another way to talk about that symmetry is to say that Bij is equal to Bji. So the element in the ith row jth column is the same as that in the jth row ith column. I know that can be a mouthful, but for example, B23 is equal to B32. So the second row, third column is -7, which is equal to the third row, second column. When we have many variables to analyze, it's sometimes a good practice to look at the pairwise correlations between variables. And you may have done this already with Dr. Labar, and you create a correlation matrix. Suppose we have 4 variables, and we'll just call them x1, x2, x3, and x4. A correlation matrix, we'll call it C, is defined so that the ijth entry of the correlation matrix gives us the correlation coefficient between xi and xj. So suppose we have a correlation matrix for the 4 variables that looks like this. The diagonal elements of this matrix, the Cii, for the ith row, ith column, should always equal 1 because every variable is going to be perfectly correlated with itself. And then in this example, I also have that the 3,1 entry, which is equal to the 1,3 entry, is equal to -0.9, and that would indicate that x1 and x3 have a strong negative correlation. And the correlation matrix is always going to be symmetric, right? Because Cij will always be equal to Cji, because the correlation between xi and xj doesn't change if I change the order of xj and xi. Here's a good slide to check your understanding. We'll come back with the solutions in 1 second. And here they are. So you'll notice if you take the transpose of the matrix transpose, we get back to the original matrix that we started with. The final topic that we're going to talk about in this introductory lesson is the idea of some special matrices. And we'll start with the identity matrix. The identity matrix is a square matrix with diagonal elements equal to 1 and all of the other elements equal to 0. The bold capital letter I is always going to be reserved for the identity matrix. And sometimes we'll use a subscript to specify the dimensions of the matrix. So I2 is a 2 by 2 identity matrix, and I4 would be a 4 by 4 identity matrix. Obviously, since the matrix is square, we only need one number to specify its size. And the columns of the identity matrix are sometimes used in different ways, and we refer to them as elementary vectors. Elementary vectors will be zeros everywhere except for a 1 in a single position. And we'll use EJ to specify the jth column of the identity matrix. And if it's the jth column, that means it's all zeros, but it has a 1 in the jth row. So this subscript on the E is going to tell us where the 1 is located. For example, E4 is a vector of all zeros with a 1 in the 4th position. Now, in this case, I haven't actually specified how long this vector is, so we have to find that out from context, or it will be specified using some of the notation that was listed before in the previous tutorial. If we use the vector E, bold-faced E with no subscripts, that's generally used to denote a vector of all ones. And there are some resources that write that as a bold number 1, but it's unconventional to really use numbers as variables to represent a vector. So in general, most sources should use the letter E, bold-faced letter E, to denote the vector of all ones. The next special type of matrix we'll talk about is a diagonal matrix. And the identity matrix is a special case of a diagonal matrix, which is square and has dij equal to 0 when I is not equal to j. So that means when the row number is not equal to the column number, the element is 0. In other words, the off-diagonal elements, those elements that are not on the main diagonal, will always be equal to 0. So here, D is a 3 by 3 diagonal matrix, and it has all non-zero numbers on the diagonal. And here, S is a 4 by 4 diagonal matrix, and it has a 0 on the diagonal, but that's okay. The only thing we really need to be sure it's a diagonal matrix is that all of the off-diagonal elements are 0. And since all those other elements are 0, to specify enough information to create the diagonal matrix, all we need to do is list those diagonal elements. So in software or otherwise, we can shorten the writing of this matrix and simply write that it's a diagonal matrix with diagonal elements as listed. And so this is actually the code that will be used to create diagonal matrices. Next, we have an upper triangular matrix, and that's a matrix that has zeros below the main diagonal. So it's upper triangular because all of the stuff, all of the non-zero stuff, happens in the upper triangular portion of the matrix. And so these asterisks here that I've used can represent any number. And they can be 0, there can be zeros up there. The only thing that's necessary is that below the main diagonal, every element is 0. Similarly, a lower triangular matrix will have zeros above the main diagonal. So all the stuff, all of the potentially non-zero elements are in the lower triangular portion of the matrix. And then one sort of statistic, you may say, I don't know, one calculation that can be done on a matrix is called the trace. And the trace is only defined for square matrices, and it's written either with the full word trace of A or TR of A. And that's just the sum of the diagonal elements. So the trace of A is the sum from I equals 1 to n of AII. So the element in the IIth position. So here I have two matrices, A and D. They're both square. So the trace of A is the sum from 1 to 3 of the diagonal elements. A11 is 3, A22 is 1, A33 is 3. And the trace of D, this is an error. That should be a 4, correct? So the sum from 1 to 4 of the diagonal elements of D, which would turn out to be 5. So here's one place to check your understanding. Write out each of the following matrices and then compute their trace, if that's possible. Finally, the solution to that slide. And one more, check your understanding. And the solution. And that's all we have for today. I look forward to the next time when we talk about arithmetic.